Hello students, in this brief lecture I will try to explain the various components of load torque. You recall the equation that we discussed earlier, the dynamic torque equation, T minus TL equal to J d omega m over dt. So today we shall discuss what are the various components of this load torque TL. The motor has to run, it has to move certain load. The motor shaft will be placed on the frame of the motor. Some bearing will be there. So always there will be some friction that the motor has to overcome. So the major components are the friction torque that the motor has to overcome. Then it has to overcome the wind friction also. So you may call it as wind torque or wind friction torque. Wind friction torque. So this is also one of the components of the load torque, and the third is the load torque required to do the useful work, that we call as T capital L. Now let us discuss one by one. The friction torque, there are various types of friction that the motor has to overcome. One type is, or one component of this friction torque is the Coulomb friction TC. This component is independent of speed. It remains constant at all the speed. So if I show it on the graph, it will be looking like this. It is speed on this axis and the Coulomb friction on this axis. So this Coulomb friction torque remains constant at all speeds like this. But as you know, friction torque always opposes the motion. As the speed reverses, the torque will also reverse. So in the negative speed, the value remains same, but its direction is opposite. So positive speed, the Coulomb friction torque is positive and constant. For the negative speed, it is again constant, but it is negative. The second and the major component of the friction torque is the viscous friction torque, and this torque will be proportional to speed of the motor. Tb is equal to B times omega n. B is a constant that will be called as viscous friction coefficient. So as you see, it is linearly dependent on the speed. So if you I show it on the graph, it will be somewhat like this. Speed, viscous friction torque. So it will be linearly depending on speed like this. At zero speed, torque is zero. For positive speed, the torque increases linearly and it remains positive. For negative speed, it will become negative. The third component of torque is known as static friction torque, TS. And this is present, as the name suggests, it is only present near static condition, near zero speed. Whenever you push something, if you try to push some table, in the beginning the force required is higher, but as the table starts moving, the force required to move it reduces. It is because of some additional force required to move during starting. So that torque that the motor has to overcome is known as static friction torque. If I show it on the graph, it will look like this. The speed here is static friction. So this is present only at zero speed. As the speed increases, this reduces and vanishes at certain speed. Similarly, in the negative direction also, it is present at zero speed. As the speed increases, it decreases and vanishes at certain speed. So these are the three components of the friction torque. If you combine all these friction torques, you will get a curve like this. This you can call the net friction torque that the motor has to overcome. friction torque Tf. So it is like this. In both the directions, curves are identical. So this is the net friction torque that the motor has to overcome. The second component of load torque that the motor has to overcome is the wind friction torque. When the motor rotates, it has to overcome the wind friction. The wind opposes the motion. Higher the speed, more will be the position of the speed of the wind. So this wind torque, the wind friction torque, is proportional to square of the speed. So Tw is equal to C omega m square. The third component is the torque required to do the useful work. The motor is employed to move some certain things. It has to move some trolley, it has to move some train, it has to move certain pump, it has to move or blow certain amount of air. So these are the torques that will be required to do the useful work. So these are the various components of the load torque. Now let us combine it and see what is the total equation. So the net torque that the motor has to overcome is the net torque TL. You can write by combining all these components. So first it is the friction torque plus the windage torque plus the load torque TL. Now let us break up into various components of TF. So TF includes TC plus TV, the viscous friction, and then the static friction TS. So this is the total load torque. We can write these equations, these components in terms of speed also. So if you write it like this, TC, TV can be written as B omega m, TS, let us write it as it is, TW is C omega m square plus TL. So these are the various components of load torque in terms of equation. So the total load torque can be written like this: Coulomb torque plus the viscous friction torque, static friction torque, wind friction torque, and the total load torque required to do the useful work. Out of these various components, the major component which is present is the viscous friction torque and the torque required to do the useful work. Other components, that is Coulomb friction torque and wind friction torque, are small as compared to TL and B omega m. This static friction, it is present only in the beginning near zero speed, and when the motor is running, the load is running, load is moving, then this torque is not there. So this is not considered in dynamic analysis. So you can neglect TC and C omega m square and TS for dynamic analysis. The value of B can be increased slightly. So you can write the equation like this: TL is equal to B omega m plus TL. So value of B can be increased slightly to take into account the effect of Coulomb friction and wind friction torque. So this simplifies our analysis. So this equation, it is reduces to TL equal to B omega m plus TL. Now let us try to put this equation in equation number 1. So it looks like this: T minus TL, that is equal to B omega m minus T capital L is equal to J d omega m over dt. Now this equation, let us write it slightly different way. So T minus TL, you can write it as B omega m plus J d omega m over dt. As I said earlier, the load torque is the torque required to do the useful work. The nature of this TL depends on the application. In some cases, the load torque is constant load torque. For example, the case of a lift, as we discussed earlier, there the torque depended only on the force due to gravity, acceleration due to gravity, and the radius of the pulley. It does not depend on speed. So suppose that the load torque TL is constant load torque. So this T minus TL, we can give some name to it. Let me call it T net is equal to B omega m plus J d omega m over dt. Now this equation that we have just written, you can compare this equation with one familiar equation in electrical circuit. You recall one electrical circuit where we apply a voltage V to a series combination of R and L. That is simple series RL circuit. When we close the switch S, a current flows here, I, and the KVL equation that you write there is Ri plus LdI over dt. You compare these two equations. You can see that these equations are exactly similar. Here T net in the new equation that we have just got is analogous to the voltage of the electrical circuit. The viscous friction coefficient B is analogous to resistance R. The moment of inertia J is analogous to inductance L of electrical circuit, and the speed in the mechanical circuit is equivalent to current in the electrical circuit. You recall that what is the solution of this equation? We write the current I as V upon R 1 minus e to the power minus t upon L by R. This L by R we call as time constant. Let me call it as tau E, time constant of electrical circuit. Time constant of electrical circuit. Or you can say the electrical time constant of the circuit. Similarly, you can write the equation of this equation as omega m is equal to T net upon B 1 minus e to the power minus t upon J upon B. Again, this is a constant J upon B. You may call this constant as tau m. That we may call as mechanical time constant of the system. This V upon R is the steady state current. So this T net upon B you may call as steady state speed. This V upon R we may call as steady state current IS. If you plot current with respect to time, the curve looks like this. Time, current I, current rises initially, and finally it saturates and it becomes constant, and this value is equal to V upon R, that we call as steady state current IS. Similarly here also, if you plot speed with respect to time, the speed will rise initially linearly, then it saturates to steady state speed omega ms, that is T net upon B. So what is this time constant? Time constant indicates how fast the current will rise. More the value of time constant, the more the time will be taken by the current to reach the steady state value. So if the time constant increases, the curve becomes like this. If time constant decreases, it becomes like this. So lesser the time constant, lesser the time the current will take to reach the steady state value. Similarly here also, if you increase the time constant, the motor's speed will increase slowly and it will finally reach the steady state speed. So the more the mechanical time constant, the slower the speed will reach the steady state value. So this mechanical time constant and electrical time constants are analogous, but their values are different. Electrical time constant may be some milliseconds, maybe 10 or 20 milliseconds, whereas the mechanical time constant tau m, it may be some tens of seconds. So it may be from say 20 seconds to say 60 seconds. So mechanical time constant is much higher than the electrical time constant. Electrical time constant tau e, it will be in the range of some 10 to say 20 or 30 milliseconds, and here it is in seconds. So what does it mean? This means that whenever you do some changes, for example, you are giving some DC supply to some DC motor, you change the voltage, the current will change instantaneously because the electrical time constant of the circuit is very small. Within say 10 to 20 milliseconds, current will reach the new value of current as per the applied voltage. But as the current increases, the motor torque will increase, the speed will increase gradually, and it will take certain time for the motor to settle to new value of the speed. So this mechanical time constant is much higher than the electrical time constant. Later on, we shall study one more time constant that we call as thermal time constant. When we start a motor, put the load on the motor has some certain losses, iron losses and copper losses. Because of those losses, the heat is generated, the motor's temperature starts rising, and finally the motor reaches certain steady state temperature rise. So this rise in the temperature of the motor, it takes longer time, and the constant that governs the rate of rise of that temperature is called thermal time constant, that we shall discuss later in the later part of this unit. So now we shall have three types of time constants. The smallest one is electrical time constants in the range of some milliseconds, the mechanical time constants in the range of some tens of seconds, and the thermal time constants, it will be in the range of some minutes, tens of minutes, 20 minutes, 30 minutes, 40 minutes, like that. So these are the different types of time constant that you will encounter in this course. Now there are various types of loads that the motor has to drive. As I said earlier, some loads are speed are producing speed dependent torques, and some are constant speed torques. So let us see what are the various types of load. So broadly you can classify the load torques as constant torque load and speed dependent load torques. Constant torque load, for example the low speed hoist. We discussed earlier also the case of a lift or a hoist where the load torque was because of the acceleration due to gravity. On the drum or pulley on the one side we had the counterweight, on the other side some cage was there. Suppose the cage is empty, the weight of counterweight is more than the weight of cage, so net torque is acting downward. This is the torque produced by this counterweight, this weight multiplied by R, minus the torque produced by this cage, that is weight of this cage multiplied by the radius. So, and the weight depends on mass and acceleration due to gravity. So here the torque is a constant torque load. It does not depend on speed. So one example of constant torque load is low speed hoist. At high speed, when the speed becomes high, the windage friction or windage torque comes into picture and the torque starts increasing. But at low speeds, the windage torque is negligible, viscous torque is also negligible as compared to the gravitational torque, so the net torque can be considered to be constant. Similarly, in the paper mill drive, there are various torques acting, but the most dominating torque is the Coulomb friction torque, and that is constant. So this can also be considered as an example of a constant load torque. Now let us see what are the different speed dependent load torques. One example is fan or its compressor, blowers, aeroplanes. In these loads, the actual load is the wind. For example, a fan, ceiling fan or a cooler fan, it has to push air. So the load is the wind. Higher the speed you want, more torque you have to produce. So this torque depends on square of the speed. It can be shown like this. So this is load torque, and as the speed increases, the load torque increases rapidly. It depends on square of the speed. And the high speed hoist, that is lift, at low speed the torque was only because of the gravitation torque. But as the speed is increased beyond certain value, the wind friction torque, which was present even at the low speed, but it was negligible, at high speeds it becomes considerable, and the total load torque starts increasing after certain speed. So this high speed hoist can also be considered as an example of speed dependent load torque. Similarly, the traction load, the train or the trolley or the car, in the beginning static friction is there, and as the bike or the train catches the speed, the load torque first decreases because static friction is decreasing. After certain time, certain speed, static friction disappears, and the other components of the friction, that is the viscous friction and the wind friction, they start increasing, and as the speed increases, the torque also increases. So in this way you can classify the various loads as constant torque load and speed dependent load torques. Now there is one more classification of the load torque that I will discuss just now. So now we can classify the load torque on the basis of whether the load can move the motor or not. So depending on that, we can classify it as active and passive load torques. Active load torque. The loads which have capability or potential to move the motor is called active load torque. And they will always have one sign, either positive or negative. They do not change their sign on speed reversal. For example, the gravitational torques. Let us recall the case of a lift, where on one side we have the counterweight, on the other side the cage, and the weight of counterweight is more than the weight of the cage, empty cage. And suppose you have to move the cage downward, so you have to apply a torque from the motor in the clockwise direction, so that to overcome the load torque. So this is a motoring case, but if you stop the motor, or you don't give the supply to the motor, the torque produced by the motor becomes zero. In that case, the lift will start moving upward by the gravitational load torque. So the speed will reverse, but the load torque will always be in the same direction. Now the load torque has the capability to move the lift by itself. So such a torque is known as active load torque. It can move the motor. So in first case, speed was clockwise, the load torque was anti-clockwise, but here speed has reversed, but load torque is in the same direction. It doesn't change its sign. So such a torque is known as active load torque. Similarly, the case of tension and torsion of elastic bodies. For example, let us take the case of a spring which is attached to some object, some block. So this is a neutral position. If we push the block like this by applying a force, the spring force will oppose the motion. It will act against the force. But if we remove the force, now the spring force is again in the same direction, and it moves the block in the opposite direction. The direction of motion of the block has reversed, but the force applied by the spring remains the same. So such torques which can drive the motor are called active load torques. The other and the more common load torques are passive load torque, which always oppose the motion. If you have to move some certain object from one position to the other position, you have to apply a force. If you want to move the object in the other direction, the force has to be reversed, and the friction force will also oppose the motion. So such a force always oppose the motion and change their sign on speed reversal. So examples of this type of torques are torque due to cutting, windage, friction. In all this type of load, fans, blowers, compressors, etc., they always oppose the motion, and they may be classified as passive load torque. So this is all for today's lecture. Now in the coming lecture we shall see that how the characteristic of load will affect the dynamics of the system. You have studied induction motor characteristics. You have seen that some part of the characteristic is stable characteristics, stable region, the other is unstable region. Why it is so, and how we can operate the load such that the point of operation is stable operation. So we shall discuss this in the coming lecture. Thank you for today.